What's up, guys? Today we're going to be talking about reaction rate, constant, and reaction order. So we're going to be talking about those specific concepts in kinetics. So it's kind of like an introduction, and we're also going to go through some practice problems with finding the reaction order. So let's start with the reaction rate. So what is the reaction rate? Well, there's this little thing called the collision theory. So it's collision theory. And this theory pretty much states that the reaction rate is proportional to the number of collisions per second or per seconds. So reaction rate is showing us the number of collisions for over time. So reaction rate, we could also think of this as the rate in which the reaction is occurring. So if we have a high reaction rate, that means that the reaction is occurring at a faster rate versus a low reaction rate. Well, it's not happening at a very fast rate, happening at a slow rate. So that's sort of reaction rate. And if we can sort of visualize this, we have some molecules over here. And if we were to have a high reaction rate, then these molecules would be colliding with each other continuously, going back and forth, clashing against each other, and we'd have a lot of collisions. So this might show a high reaction rate. But over here, if we did that same thing with the molecules, sort of visualizing them, and they were barely colliding, like barely at all, not moving that much, then we'd have a low reaction rate. Now, what about for a reaction? What needs to occur in order for a reaction to happen? So for a reaction to happen, we need kinetic energy. So I'm just going to put an arrow right here. So we have kinetic energy. And if we remember, kinetic energy is just the energy of motion. So this is energy of motion. And the reason why we need kinetic energy, or at least a sufficient amount of kinetic energy for a reaction to happen, is because this kinetic energy is turned into vibrational energy. Vibrational energy. And what is vibrational energy? Well, vibrational energy is the energy responsible for breaking bonds. So we have breaking bonds. And for a reaction to occur, we need to break the bonds of the reactants in order to form the products. So here's how it goes. For a reaction, we need a sufficient amount of kinetic energy. So we need a sufficient amount of kinetic energy in order for that to turn into vibrational energy. And enough vibrational energy will result in breaking bonds. So the most important thing for a reaction to happen is that we need enough kinetic energy. Now, another thing that for a reaction to occur is that we need the proper orientation or the proper alignment. So why is this important? Well, if I drew a sort of model right here, and let's say we had this one green molecule and another green molecule, but that green molecule is binding to a red molecule and maybe even a blue molecule and then a red molecule right there. So the proper orientation for this reaction would be the green binding to the green, and that would form these two green molecules, and we'd have our blue and red molecules. So this is what a proper orientation for a reaction must look like. So a proper orientation is necessary in order for these reactants to turn into the products that we want. So proper orientation is very important for a reaction to occur. Because let's say, for example, and if we copied the same scenario, but instead of the green molecule hitting the other green molecule, hits the red molecule, well, nothing would happen because they're not in the proper alignment. They're not in the proper orientation. So that green molecule isn't binding to the other green molecule. And sort of a simplified way of saying that, but we just need proper orientation in order for a reaction to occur. Okay, so now we know that. What about activation energy? So what about activation energy? So what is activation energy? Well, activation energy is the energy necessary for a reaction to occur. So we need sort of a threshold of energy in order for a specific reaction to occur. So if we were to draw a sort of graph detailing what activation energy may look like, just draw something like this in another straight line right here. So this line over here is our reactance. And over here, that peak right here is known as the transition state. Transition state. And this is the intermediate form of those reactants and products that's like kind of before, after the reactants, but before the products. So now I'll show you a quick image of what that may look like. Then we have products right here. So if we go back to our sort of green and blue molecule example, I'm just going to copy, paste this. So right here, this would represent our reactants. So I should draw like a sort of plus sign right here. But this is our reactants. And those reactants will go into the transition state. So that transition state, I'm going to copy this. Transition state is going to look something like this. So as you can see, it's like the intermediate form of what we might see. So that green molecule is binding to the other green molecule. That's our transition state. And over here, we would have our products. And that's what we end up with. So I'll just put a plus sign right there. And that's our products right there. Now, another name for the transition state is also the activated complex. So activated complex. And as the name pretty much says, when we get to this peak, that's when the reaction is sort of activated. So that's why it's kind of called the activated complex. Now, from the peak of our diagram all the way to the reactants side, so all the way to this line over here, that is the activation energy. So when you're trying to find the activation energy, it's from the peak of this diagram all the way to the reactants. And that is our activation energy, which is the energy necessary for the reaction to occur. Now, talking more about reaction rates, what does that look like? If we were asked, like, what's the average reaction rate? How do we even find that? Well, let's just go off this sort of basic equation. So it's A that turns to B, where A is our reactant, B is our product, and this is just representing some concentration of a molecule. So the rate of this, or the rate or average rate, whatever you want to call it, the rate would be negative delta, the concentration of A over delta time. It could also be the delta of concentration B over delta time. So the reason why we made this A negative is because we're decreasing in reactants. We just put a sign on it. But when we go from left to right, we're going from reactants to products. And that's why our A is going to have a negative sign, because we're decreasing in this variable. So when we do that change, the change in, so change in is final minus initial. And our final is going to be smaller than our initial, which produces a negative number. And that's why we have a negative over here to counterbalance that. So we get a positive number, because rate can't be negative. It's always going to be positive. So because final is going to be less than initial, we get a negative number. So negative times a negative gets us a positive. And that's why A is going to be negative, because it is decreasing going left to right. And B is going to be positive because it is increasing going from left to right. So now we know that, we have to understand that one of the things that affects rate is temperature. Well, you might be wondering, how does temperature affect reaction rate? Well, when we increase temperature, we increase the reaction rate because we're getting more molecules that have a sufficient amount of kinetic energy that can break bonds. Or in other words, we're just getting more molecules that can get more kinetic energy, turn that to vibrational energy, break the bonds, and result in a reaction. So with an increase in temperature, we're having more molecules be able to go with the reaction. Now let's look back at our chemical equation, and we really have to account for these stoichiometric coefficients because they're very important in looking at what the rate is for each of these. So we have 2 of thiosulfate, 2 of iodide. So one of the equations that you should be familiar with is rate equals 1 over A and then delta A over delta T, that should be negative, equals negative 1 over B, and then delta B over delta T equals 1 over C, and we have change in C over change in T, and that also equals 1 over D, and be something like this. And this is basically assuming that our equation is A plus B goes to C plus D, which is sort of the model that we're using over here. So then for the thiosulfate, and I'm not going to write the entire thing, negative 1/2, and then the thiosulfate S2O3 2 minus, and we have that delta T, which equals 1/2 of our iodide over delta T, and that would be sort of the rate for this reaction. All right, so now let's talk about rate law. And first off, what is rate law? Well, rate law basically describes our sort of reactants. So it's rate equals K, then we have parentheses A to the X power times parentheses B to the Y power. And these X's and Y's, they represent our reaction order. And our K over here is our rate constant. So this is what the rate law looks like. And these are our reactants. So this is basically if our equation was A plus B goes to C plus D, this is what our rate law would look like. So if we were to draw a sort of table relating reaction order to the units of K, so we'll do this, rate law, what that would look like as the rate law, and then the units of K, let's say we had a reaction order of 0, or the 0th order, then our rate would equal just K, because if we have, we could write it like this as well, but A to the power of 0 is just 1, so, and 1 times K is just going to be K, so that's pretty much unnecessary information. And our units would be M times seconds to the negative 1 power, or you could also write it as M over S. Now for the reaction order for the first order, then we'd have a rate that equals K times A, or K times B, if we're looking at this equation over here. And our units for K would be seconds to the negative 1 power, or 1 over S. So for the second reaction order, we would have something that might look like rate equals K A squared, or K B squared, or A times B K. Apologies for the bad handwriting. And for the units for this one, it would be M to the negative 1 power times S to the negative 1 power, or 1 over M times S. Now for the third reaction order, or the third order, then our rate would be K to the A squared B, or it would be B squared A, and it could also be A times B times C if we had a third reactant, but that's a little bit more rare. So the units for this one would be M to the negative 2 power times seconds to the negative 1 power, or it would be 1 over M squared S. And as you can see, the units of K really depend on the reaction order. And this is the overall reaction order. The overall reaction order is basically X plus Y equals the overall reaction order. So if we look back to our examples, we had 2 over here and we had 1. Those reaction orders are 1. We just don't put 1 because it's just unnecessary. But 1 plus 1 is 2. That's why the reaction order is 2. And then 2 plus 1 is 3. That's why the overall reaction order is 3. So now let's go through a quick practice problem that I actually found from ChatGPT. So you can definitely use ChatGPT towards just making any practice problems you want. Sometimes it doesn't give you the right answer, which kind of sucks, but it is one of the best resources that you can use to make a practice question. So let's look at this question. So it's giving us the rate law, which we already know what that kind of looks like. They put M and an N, but we just did X, Y. It really doesn't matter which variable we use. But when finding the reaction order, it's always determined experimentally. And that's why they've given us experimental data, because that is the only way to find reaction order. So the question asks us, using the provided data, determine the reaction order of hydrogen peroxide, the reaction order of iodide, the overall reaction order, and the rate constant for the reaction. So when you're doing a problem like this, we first want to start with hydrogen peroxide. And the only way to find the reaction order of hydrogen peroxide, or to even start, is to looking at the experiments where iodide is the same number. So it looks like that's experiment 1 and experiment 3. Because as you can see, the iodide is 0.1 and 0.1. So in solving this, we first start with the concentration. So this is 0.2 over 0.1 for a hydrogen peroxide. And I think that should equal 2. And since we know that information, now we can look at the initial rates. And initial rates are basically the instantaneous rate at time 0. So that's the initial rate. And so we have to copy the same sort of formula. So this was experiment 3 over experiment 1. So we have to do the same thing. 1.0 times 10 to the negative 2, which is experiment 3, over 5.0 times 10 to the negative 3, which is experiment 1. And when we do that math, that'll be 1 times 10 to the negative 2, 5 times 10 to the negative 3. So that's 0.01 divided by 0.005, and that gets us 2 as well. So both of these numbers are the same. They're both identical, and that means that this is first order. Now, if we had 2 over here, and let's just say, just for this example, that we had 1 over here, that would be 0 order, because we have double of the concentration than compared to the initial rate, so that would be 0 order. And if we had something like the initial rate is double of the concentration, that would be second order. So those are 2 important things to know about first order, 0 order, and second order. So we know that our hydrogen peroxide, H2O2, is in the first order. Now what about iodide? Well, let me sort of erase this. And we need to find the experiments in which the hydrogen peroxide is the same value, which is experiment 1 and experiment 2. And our iodide is 0.1. So, I mean, we already know 0.2 over 0.1 is 2. And we're pretty much using the same values. So 2 equals 2 in first order. So iodide is first order as well. First order for iodide. And the reason why is because the iodide experiments, the experiment 2 over experiment 1 is just pretty much the same exact values as the one given from the hydrogen peroxide. So now that we know that, what is our overall reaction order? Well, let's actually write our rate law. So our rate law would equal K parentheses H2O2 and parentheses iodide. And those are both first order. So if we kind of wrote those ones, it would be 1 plus 1 equals 2. So that's why the overall reaction order is second order. Now that we know that, how do we calculate the rate constant for the reaction? Well, what are we actually given? We're given the initial rates and we're given the concentration. So for this one, we could choose whichever experiment we want. I'm going to choose the first experiment. So we know our rate. So our rate is 5.0 times 10 to the negative 3, and that equals K. And if we move this over, just divide that over, we're going to have 0.1 times 0.1, which should get us our K. And it will be 5 times 10 to the negative 3, and 0.1 times 0.1. So 0.005 divided by 0.01 is 0.5. So K should equal 0.5. And if you wanted to check this, because K should be constant for everything else, you can try using the rate law and see if you get the same rate. So if we use experiment 2, it would be 0.1 times 0.2, and then our K would be 0.5, and that should get us 1 times 10 to the negative 2. So 0.5 times 0.1 times 0.2 is, 0.01, which is this value, and that's when you know your K is correct. So just like double checking, when you already found your rate constant, go through at least 1 or 2 of the experiments and see if you get the initial rate, if you get the same initial rate that was experimentally determined from your concentration of the H2O2 and your concentration of iodide. So that pretty much wraps up this video on reaction orders, constant, and rates, and we'll dive more into those topics, but this was sort of a introduction to those topics. Hopefully you guys learned something, and as always, a Pomodoro a day will make you a doctor someday. I'll see you guys in the next one.